Okay, this is the first class of the mathematical modeling class of the spring semester of 2012. I have uploaded the syllabus here first, and also I have made some notices. Let me show you the first notice of this class. Okay, introduction of our mathematical modeling class. Here, I mentioned the meaning of the mathematical modeling, and also I mentioned on my office hour and my office number, which is 32304, and here's my phone number. I have fixed 1 hour of my office hour on Thursday from 3 p.m. to 4 p.m. And we will fix another extra hour after the first week of this semester. You may leave a note on your preference on this extra hour of office hour in this semester in Q&A. And also, we're going to use the textbook. Our main textbook of this course is the Mathematical Modeling with Microsoft Excel by Nurwich and Dean Argenbright. You will find the comment on this textbook on this website. And also, in order to deal with the mathematical modeling, we need some background of mathematical knowledge. So, we will refer the matrix analysis book by Roger Horn and Charlie Johnson. So this will be a ground for the linear models. And also, you will have a freedom to do the non-linear modeling with any other book on other discipline. Okay, here is, okay, yeah, so we will meet on Monday and Thursday in this E-Plus lecture room, and also we will have an office hour here and another extra hours on some of these spots. And also, you will see some more information on our class in this informations with the web addresses, which I will show in the first lecture soon. And also, I have uploaded some of the files that will be used as a prerequisite and the pre-knowledge for this math modeling class. This PDF file was protected by a password 4321 here. So you just type 4321 there. Then you will be able to the full file of this preview and review and preview for this course. This is chapter 7 of the book Mathematics Form and Function by Saunders McLean. You can easily read the the whole content of linear algebra from the beginning to the end in the way of just reading the content, not the way of the definition, theorem, and proof and examples. Instead of that, you will just go through what's the meaning of the linearity and what's the origin of the linearity and all the concept and definitions of linear algebra, including linear combination and span and subspace and linear independency and basis and dimension and linear transformation and additivity and endomorphism and examples of linear transformation such as differential operator and integral operators and vector space with infinite dimension and functional spaces, which is an example of a vector space, and the relationship between the homogeneous system of differential equation and the system of linear equations, and duality and tangent space, and the fundamental theorem of algebra, and field and groups, etc. The second section deals with the comparison of matrix and linear transformation. This shows how the matrix is defined and what is the relationship between this matrix and the linear transformation. And it will end the theorem on matrix representation of linear transformation. In the process, you will see the rank nullity theorem and the composition of linear transformations and other properties of the matrices, which is same as the properties of linear functions or linear mappings, and singularity and non-singularity of the linear transformation, which is equivalent to the non-singularity of the matrix, and a multiplicative property of matrices and determinant, which is this. Okay, and also you will see the meaning of the affine transformation, etc. In section 3, you will see the meaning of the eigenvalues and similarity between the matrices and the definition of eigenvectors and an important theorem on the matrix diagonalization that you already know. The if and only if condition, a matrix to be diagonalizable, is the matrix has the full number of linear independent eigenvectors. Okay. You know how to prove this one. But in here, the proof is written in a way of talking in the story. And also, characters equation and fundamental theorem of algebra, and Cayley-Hamilton theorem, and dual spaces, and bilinear functions, and tangent space and cotangent space. And natural isomorphism, which lead you to the dual spaces from a given vector space V. On the set of on a vector space, if you define a linear transformation, then you can define the dual space from there. We did linear transformations on the vector spaces. So this gives you the different vector space from a given vector space. And the linear transformation is a study on investigating the properties on those relationships between vector spaces and the linear transformations. So you can just go through it by reading it. Inner product space is on section 5. And Gram-Schmidt's orthogonalization process is the main part of this section. And orthogonal matrix is the next section, which is a special case of a unitary matrix in a complex matrices. And adjoint transformation is dealt in section 7. And principal axis theorem is on section 8. Here you will see the general form of the quadratic forms in the elementary linear algebra. Okay. And bilinearity and tensor product, which you didn't see it before. So you can just go through it. Tensor was a very important part of linear algebra before, and still very important in physics. But nowadays, the importance of tensor is not as big issues in the linear algebra, because there are more things to do in linear algebra nowadays. Before, when we study only theories, when we covered almost on the theory of linear algebra, then the next step was a general form of those which lead to the study on tensor. But now more areas of linear algebra has been developed, including numerical linear algebra and computational mathematics, which was a new area. So more interest is given on those new areas over the old theoretical areas such as tensors. Yeah, you must be very familiar with those kind of diagrams, which is shown in abstract algebra. This is the old general form of those things, which is direct in the matrix theory. Okay, so you just go through it by reading it, and then this is a counterpart of normal subgroup in group theory. All of these approaches and the knowledge on normal subgroups are used in the matrix theory. It's a natural generalization of all those abstract algebra to the matrix theory. So there are many things that you can do after you had a solid background of abstract mathematics, including after linear algebra, differentiation and reanalysis, abstract algebra and geometry, topology, and all other courses are done, then you can restructure all of those knowledges in the terminology of a matrix in this way. Okay, so all of those are the part of the matrix theory. And extraordinary algebra and differential forms that you have seen from the differential geometry. These are also a part of the matrix theory as well. Okay, but some of you are now started taking on those courses, so we will just give you the brief review of all those knowledges of the basic undergraduate and master's level math courses. And those are all combined in the way so you can just read it in this way. Okay, and this is the kind of matrix that you're going to see. This is an example of companion matrix. This is a very important part on the study of the similarity. Okay. And also companion matrices and direct sums, etc. In the last section, section 13, there's a brief abstract of what has been treated in chapter 7. And here, it tells the meaning of linear algebra in late 20th centuries. Okay, the author of this book, The Mathematics is Form and Function, is a Saunders McName. He is the one who created the category theory, which is an attempt to explain all disciplines of mathematics in one terminology. And this section shows how all modern mathematics is combined in a way of linear algebra. So you just go through it to understand what you are